Hey everyone, it's Jamie Batts, your instructor for A&P2. I am about to start the lecture for Chapter 21. This is the second part of Chapter 21 that covers the respiratory physiology, a little bit more intense than the first part, which was just the anatomy. So I do have a bunch of little things I'm going to be asking you to draw and kind of map out on your own. I'm trying to wean you away from me drawing it for you, and I want you to go through that process of trying to map it out on your own. Here's why I want you to do that, because you're going to start to get a little frustrated as you draw and try to figure out exactly what I'm telling you to do. And that process of getting frustrated and figuring it out is going to help you learn it and remember it, which is what this is all about, right? So, again, not trying to be mean or lazy, just trying to help you with your learning. So, let me switcheroni here to the screen share mode. And here we see Chapter 21, which this is from the Harvard Community College textbook that we're using, the Martini textbook. So, and I apologize, I'm just coming back from the gym and just trying to squeeze this lecture in for you guys today. So, we're going to start by talking about what respiration is. Respiration is actually two processes. There's an internal respiration and an external respiration. The external respiration is the exchange of gases between in the inside of our body and the external environment. So this is what's happening in the lungs, this external respiration. It involves pulmonary ventilation. Pulmonary ventilation is the technical term for breathing. This is physically moving the air into the body and then exchanging those gases with the interstitial fluid of our blood, right? Movement in and out of air, into and out of the alveoli, as well as into and out of the capillaries is what external respiration is all about. Pulmonary ventilation is the act of breathing that brings that air in and out of the body. Our internal respiration is what's happening on the other side, right? So you get these gases into the blood, right? Oxygen specifically. We get that oxygen into the blood at the alveolar capillaries, and then that blood travels through the body, goes to everywhere, and the process of internal respiration occurs. Internal respiration is where that oxygen is then absorbed from that blood into the tissues, and the tissues exchange carbon dioxide, putting carbon dioxide back into the blood and allowing that to go back to lungs, where external respiration can occur, and so on and so forth. It keeps on going. So there's two processes involved in respiration. So we, of course, have this process of gas diffusion. We're going to be talking a little bit, actually a lot, about some physics laws and chemistry laws here in this chapter. We have this idea that this gas is going to diffuse across the respiratory membrane and across the capillary walls. So the gases that you're breathing in have to go from the inside of your lung surface to the inside of your blood across that respiratory membrane that we talked about in the last section of this chapter. And then in the blood capillaries, it has to go from inside the blood capillaries into the interstitial fluid and into the cells of our periphery. So the transport of gas is obviously essential in order for the respiratory function to occur. You have to have that blood functioning and taking those gases away. So this brings about this very intimate relationship between our cardio, our heart and our blood, the cardiovascular system, and our respiratory system. Those two are very intertwined, which is why they have this very close relationship in our thoracic cavity. This is why our heart rate and respiration rate are always closely monitored together. One goes up, the other goes up, one goes down, the other goes down. There's this intimate relationship that we'll look at as we move through this chapter. So this is just a nice visual for you so you can understand what external and internal respiration are. External respiration is happening at the lungs, starts with pulmonary ventilation. Internal respiration is happening in the periphery. So let's talk about respiration in general and some abnormalities that can occur. You have something called hypoxia. Hypoxia is when you have low oxygen levels within a particular area. This can put a limit on the metabolic activities. This is typically a localized event. So hypoxia would be occurring in a particular area of the body. When it occurs in the brain, that's very, very serious. Anoxia is when you have no oxygen supply. So this could be because of a stroke or because of a heart attack. Something is preventing the blood and therefore the oxygen from getting to those specific tissues, creating an anoxic situation, which is obviously very detrimental. You can pause the video here, go back and review this introductory section to lung physiology or respiratory physiology. We're going to keep moving through. Let's talk about the relationship between volume and pressure. I told you we were going to be talking a little bit about some physics terminology and physics laws. So here's our first law. We have this thing called Boyles Law. This guy, Mr. Boyle, he invented or basically derived this equation that says there's an inverse relationship between pressure and volume. In other words, when the pressure increases, I'll switch that around. When the volume increases, the pressure is going to decrease, and vice versa. When the volume decreases, the pressure is going to increase. And it goes back to this idea of air is made of molecules, and those molecules are always zipping around, bumping into one another. And so if you take, say, 20 molecules or 20,000 molecules, doesn't really matter, the number's arbitrary, and you put them into a container, that container has a certain amount of pressure, right? The pressure is defined by the collision of those molecules on the walls, right? If we were to shrink that container with those same 20,000 molecules, the amount of colliding or collision is going to increase. Therefore, the pressure has increased. So as our volume decreases, our pressure increases, and vice versa. That's called Boyle's Law. And here's just another visual for you. You see this lovely little box, and as that volume decreases, the pressure increases, and vice versa. So, how does this relate to lungs? Well, as we are breathing, as we're going through pulmonary ventilation, right, the technical term for breathing, our thoracic cavity is increasing and decreasing in volume. So guess what that does? It creates a change in pressure. Remember what happens when we have a change in pressure? If you have a change in pressure, you're going to have movement, right? If you have a difference in pressure, an area of high pressure, an area of low pressure, or an area of high concentration, an area of low concentration, you're going to have movement. What are we trying to move in this case? We're trying to move air. We're trying to move air into and out of the lungs. So by changing the shape of the thoracic cavity, we're therefore changing the pressure. So the shape changes of our thoracic cavity is due to the diaphragm depressing and elevating, and our rib cage expanding and contracting. So how do we do that? We have some muscles that are going to help with this. As you can see in this diagram, it's showing you how that rib cage moves. You can observe this easily when you look at someone breathing when they're lying down. If you've ever watched a child sleep, you can see their chest rise and fall, and that's literally what you're seeing here, that expansion and contraction of the rib cage. So at rest, the pressure inside the lungs, which is called the intrapulmonary pressure, intra means inside of pulmonary lungs, pressure inside the lungs, and outside the lungs are the same. So when you're not breathing, the pressure inside and outside are the same. The pressure outside the lungs, or the pressure in the air around us, is called the atmospheric pressure. The pressure inside of our lungs is called the intrapulmonary pressure. When there's no pressure difference, there's no air movement. So at rest, there's no air movement. As that thoracic cavity expands, we're increasing the volume. Guess what happens when you increase the volume? You decrease the pressure. When you decrease the pressure, you're going to create a vacuum and allow that air to come in. So that expanding thoracic cavity expands the lungs, decreases the pressure, and allows the air to move in. The pleura, the parietal pleura, is attached to the actual thoracic cavity wall. The visceral pleura is attached to the lungs themselves. And the pleural fluid is that fluid in between our visceral and parietal layer. So when you have an injury to our pleural cavity and that bond is broken, if you're literally injuring that pleural lining, you're creating a system where that change in pressure cannot exist. This is a lung collapse, or I can never say the word, atelectasis. Yeah, it's the word at the bottom of the PowerPoint. Not even going to try it. I haven't had all my coffee yet. So it's super important that the pleural linings remain intact. Think about during a car accident or during some type of sword fighting, I don't know, any other injury that may occur that would cause an injury or a rupture in that pleural lining is going to be detrimental to the inflation of your lungs. And therefore, if your lungs can't inflate properly, if they can't expand properly because of the difference in pressure, you're not going to be able to bring that air in. So here you see what I'm talking about when I'm mentioning the pleural linings, the parietal and the visceral pleura. That parietal pleura is right on the inside wall of our lungs, and then our visceral pleura is right there. My dog's just sniffing around back there. So in terms of lung pressure and lung volume, I already alluded to this, it just wasn't on the slide. During inhalation, that thoracic cavity is going to increase in volume, therefore decrease in pressure. So the air is going to move in from the area of higher pressure, which is in the atmosphere, to the area of lower pressure. During exhalation, our thoracic cavity is going to decrease in volume, therefore increase in pressure, pushing the air back out into the atmosphere. So here you see our lungs expanding and our lungs decreasing in size, allowing for that change in pressure. The change in pressure is going to allow for the movement of air into and out of the body. So this pressure differential, which is literally the pressure, the difference between the atmospheric pressure and the intrapulmonary pressure, is also the pressure which is inside of our respiratory tract, right? So this is going to determine that direction of airflow. During inhalation, the intrapulmonary pressure is less because our thoracic cavity has expanded, so that negative pressure differential is going to help pull that air into the lungs. During exhalation, that intrapulmonary pressure is greater than the atmospheric pressure because our rib cage is depressed. That's creating a positive pressure differential, pushing the air out of the lungs. This gas pressure is measured in a unit called millimeters of mercury, or mmHg, millimeters mercury, Hg. And here you see this whole cycle. This is a lot of what you're going to see here in respiratory physiology mimics what we saw in cardiovascular physiology. We saw these cycles, these rhythms. You're going to see the same thing here in our lung physiology. So if we just look at this graph in the upper right corner of the screen, you'll see the pressure differential in time. During inhalation, our pressure is going down. That's going to pull the air in. During exhalation, our pressure is going up. That's pushing the air out. If we look here, this graph is called our tidal volume. The lower graph is our tidal volume. This is the actual volume of air that's coming in and out of the lungs. During inhalation, we are bringing air in, about 500 milliliters of air, half a liter, 500 milliliters of air every time we do what we call quiet breathing. That's just the breathing that we're doing right now as we're not like running or exercising or sleeping, right? And then we push that air right back out. And that's just this expansion and contraction, creating the pressure differential, which is allowing that volume of air to come in and out very passively. That's called our tidal volume. So some common units, we've mentioned millimeters of mercury. You can also use torr, centimeters of water, pounds per square inch. Typically in anatomy and physiology, we're using millimeters of mercury. That's the standard unit of measurement in A&P. I'm going to stop this video here so you can go back and review Boyles Law and some of the topics that we covered in this section, and we will continue. Stop share. Is my computer frozen? What's going on? Sorry. Don't really know what's going on here. I'm going to try to, oh, there we go. Stop share, please. Stop sharing. Maybe not. More. I don't know why my computer's not responding. I'm going to stop this video at least.